Howdy. This is the first of two videos that are going to illustrate how to graph rational functions. And in this video, I'm going to show what I would consider an intermediate example of a rational function. And in particular, for this function, what you're going to see is a function that crosses its horizontal asymptote. And you're also going to see a function that has a hole in the graph. And so let's get right to it. Let's let f of x equal x squared minus 3x over x minus 2 times x plus 2 times x minus 3. Now this one down here, I went ahead and wrote in factored form because I didn't want to have to spend a lot of time factoring. So you remember our basic framework for graphing rational functions. First we find and classify the excluded values. And once we have found and classified those excluded values using a limit, then we find our horizontal asymptotes, if any. And finally, we find the zeros. And having gotten all of that information, that should lead us to a graph. If you get all of this information and you're still a little confused about the shape of the graph, you can always plot extra points if you need to. But 9 times out of 10, you won't need to. Just the information that we get from the excluded values, the horizontal asymptotes, and the zeros is usually enough to get a good graph here. So let's take our f of x and actually use this framework right here. Group that together and shrink it down a little bit. We're going to use this framework right here to get a good graph of our function. First, I want the excluded values. And the excluded values are going to occur when the denominator is 0, because f of x fails to exist at any point where its denominator is 0. So I set this equal to 0, and immediately I see that I have 3 excluded values right here. And we're going to classify each one of these excluded values by using a limit. I'm going to start with x equals 3, actually. To find out what's going on around x equals 3, I'm going to take the limit as x goes to 3 of x squared minus 3x over all of this. And when I take that limit and check the form, my form turns out to be 0 over 0, because 3 squared minus 3 times 3 is 0. And so this indicates to me that there is a common factor that can be canceled. And when I factor the numerator, lo and behold, there is my factor of x minus 3. I'm using the alias theorem. I cancel this, and I let x go to 3, and I get the value 3 over 1 times 5, which is 3/5. What does this mean about our graph? Because I got a finite value for the limit, that indicates that as x is close to 3, the y values are going to be close to 3/5. But right when my graph gets to x equals 3, pop, I divide by 0, and the graph fails to exist right at x equals 3. and then it keeps on going from there. In other words, my graph has a hole. The coordinates of that hole are at x equals 3 and y equals 3/5. Whenever my limit gives me a finite value, the graph will have a hole at that point. Okay, that's nice. What about at x equals 2? I'll come back now and check out x equals 2. Take the limit as x goes to 2. Notice something that can be used to our advantage. Do you notice when we went through and evaluated the limit as x goes to 3 that we ended up canceling the factor of x minus 3, and we got a reduced fraction that looks like this. This reduced fraction is equal to the original f of x for every x except x equals 3. So I can treat my reduced fraction as equivalent to f of x for all of the analysis that I now do, because I've already dealt with what happens near x equals 3. So I would use this reduced fraction here, and when I do, I can see that the form of my limit is 2 over 0, indicating that I have an infinite limit. This means that I need to consider limits from left and right separately. When I consider the limit from the left, then the factored form is helpful to me once again, because now I can take a look at the signs of each of these factors. As x goes to 2 from the left, in other words, when I'm looking at numbers a little less than 2, such as 1.999, then x will have a positive sign. X minus 2 will have a negative sign because I'm taking numbers a little less than 2 and subtracting 2 from them. But x plus 2 will be very close to 4, and that is a positive sign. Putting all this together with my sign analysis, I can see that this limit right here, that this limit right here is going to be equal to negative infinity. I knew it was infinite because of the infinite form, and I knew that it was negative infinity because of my sign analysis. When I take the limit as x goes to 2 from the right, I can use the same kind of reasoning. And for all of my factors, the signs are going to remain exactly the same, except my factor of x minus 2 is really the only one I need to check, because when x is a little bit larger than 2, and I subtract 2 from it, now I'm going to get a positive value, so that I get positive infinity for this limit right here. Notice that all of the factors except for x minus 2 kept their same sign for x's very close to 2. Well, we're going to do the same. Oh, sorry, we needed to draw our conclusion. So in the case of the limit as x goes to 3, we got a finite value, and that led us to conclude that there was a hole right here. In the case of x going to 2, we got positive, negative infinity. We got infinite limits, and so that allows us to conclude that there is a vertical asymptote at x equals 2. And finally, as x goes to negative 2, again, we can use our reduced fraction here, and again we discover that the form is now negative 2 over 0, which indicates that we again have an infinite limit. So we'll split, consider limits from left and right separately. In the numerator, as x goes to negative 2, we are going to have a negative sign here. For x is close to negative 2 minus 2, it will definitely be a negative number. Now if I take x's that are a little less than negative 2 and add 2, I'll get a value that is a little less than 0. And So I have negative divided by negative times negative. F of x will have negative values for x's less than negative 2. Using the same reasoning, now approaching negative 2 from the right, all of my factors are going to give the same signs here, except that I have to check the factor of x plus 2. And if I now take a number that is a little larger than negative 2, and I add 2, I will get a number a little bit larger than 0, so that we have negative divided by negative, and I get positive infinity as x goes to negative 2 from the right. And so we draw our conclusion, which is that there is a vertical asymptote at x equals negative 2. Well, this was the hard part about the analysis. Now we get to move on to the fun stuff, horizontal asymptotes. And again, I can take the reduced fraction x over x minus 2 times x plus 2 to be equivalent to the original f of x for all x's except 3. And when I do an end model analysis, right here, the end model for the numerator is x, the end model for the denominator is x times x. Notice I can just take the end model for each factor here and multiply them. So when the dust settles, I end up with 0 as my limit there. Now, all rational functions have the same end models on both sides. And because they have the same end models on both sides, that means I can go pretty quickly to my value there. This allows me to draw the conclusion that my function has a horizontal asymptote y equals 0. And finally, I'm going to find the zeros of f of x. And again, I can use the reduced fraction because the fraction was reduced by simply taking out the factors of x minus 3, which exclude one of the excluded values, which was nice. So if I want to set this fraction equal to 0, the numerator must be equal to 0. In other words, I can conclude that x has to be 0. Let me do a quick check and make sure that x equals 0 was not on my list of excluded values. It was not. And so it is a legitimate 0 for my function. So let's take and summarize all the information that we got about our function and get ready to graph it. We found, first of all, that there was a hole at x equals 3, y equals 3/5. We found that there were vertical asymptotes at x equals 2 and x equals negative 2. We found that the limit as x goes to 2 from the right was equal to positive infinity. The limit as x goes to 2 from the left was equal to negative infinity. We found that the limit as x goes to negative 2 from the right was negative infinity. And the limit as x goes to negative 2 from the left was positive infinity. Finally, we found that we had a 0 at x equals 0. If we take all of that information now and put it together on the graph, then we are going to, first of all, draw our asymptotes, because x equals 2. And for x is close to 2, my graph goes up on the right, down on the left, according to the limits that I got right here. Then I can draw my asymptote, x equals negative 2. And according to my analysis, my graph is going to go up on the left and down on the right, according to these limits right here. that was done. Yes, let me go back and check. Now see, anybody can make a dumb mistake here, and so sometimes we want to check. We go back and look at our limits. Aha! Limit from the left was negative infinity, limit from the right was positive infinity, which is the opposite of what we said here. So these signs are wrong, and that is going to give us a graph that makes more sense. So, up on the right and on the left, according to the limits that we found here. Our horizontal asymptote in both directions will be the one x equals 0. And finally, we have 1, 0, which is at x equals 0. And there it is. And now armed with this information, we have enough information to make a graph. We're going to take our, let's do the middle section first here. We're going to take our graph coming from negative infinity. It has to go up through 0, and it has to continue on up to positive infinity. Take the section on the right, this graph has to come down from positive infinity, and it has to head towards 0. I know that it will not cross over out here, because if I did, then f of x would be 0, and it only has 1, 0, which is at x equals 0. And finally, this piece right here is when you approach the horizontal asymptote there. I want you to notice that here, f of x crosses its horizontal asymptote at x equals 0. So this is a good example of a rational function that crosses a horizontal asymptote. Well, I hope this was helpful to you. If you